All right, hope everybody's had a good spring break. We're going to get started again on medians and altitudes. We're talking about triangles here. And I've already got your first two answers up there because of spring break. I wanted to give you a break. Are three diameters of a circle concurrent? Yes, they are. Are two diagonals of a rectangle concurrent? No. And finally, is point C at the right point of concurrency? Remember, point of concurrency is where three or more lines come together. So the answer is yes. Now I know how this thing's working. Okay, so let's continue on. Our review word for today, vocabulary, is median. A median of a triangle is a segment whose endpoints are at a vertex and the midpoint of the opposite side. So it's not an angle bisector, even though it cuts an angle into two separate angles, but it is cuts the side opposite that angle in half. So a median of a triangle is a segment whose endpoints are at a vertex and the midpoint of the opposite side. So it's similar to an angle bisector. It's kind of like an angle bisector and a perpendicular bisector put together, even though it's not perpendicular, but you got the idea. It does cut the other side into half. True or false? The median of a triangle is a segment that connects the midpoint of one side to the midpoint of the adjacent side. That is false. That would be a mid-segment. The point of concurrency of the medians of the triangles is where they intersect. That's true. And a triangle has one median. That's false. Of course, it has three medians. So circle the drawing that shows median AD of triangle ABC. So AD on the right is an angle bisector. AD on the left is the one we're talking about. That is the median. All right, so concurrency of medians theorem, theorem 5.8. The medians of a triangle are concurrent at a point, the centroid of the triangle. So now we've learned a new term. Centroid is where the medians all come together. That is 2/3 the distance from each vertex to the midpoint of the opposite side. So what does that exactly mean? In our picture, that means that DC is 2/3 of DJ. EC is 2/3 of EG. And FC would be 2/3 of SH. So the entire segment of the median, that centroid point, is 2/3 the entire median. So let's continue on. That's concurrency of medians theorem. So finding the length of the median. In the diagram at the right, ZA is 9. What is the length of CZ? So point A is the centroid of triangle XYZ, and we want to find the distance of CZ. All right, so ZA equals 2/3 of CZ. We know that ZA equals 9. Still want 2/3 of CZ. Now we're going to multiply both sides by the reciprocal of 2/3. So 9 times 3 divided by 2, and then 2/3 times 3 halves times 2/3 gives me 1. So CZ will equal 27 halves, or 13.5. So the formula here is basically if the median to the centroid point to the vertex point is 2/3 the entire median. An altitude of a triangle is the perpendicular segment from a vertex of the triangle to the line containing the opposite side. So here we're talking about, again, it's coming out of the vertex, but it's going to be perpendicular to the line opposite. Okay, so again, it's cutting the angle into two separate angles. It's perpendicular to the line opposite, but it's not a perpendicular bisector because it doesn't cut it in half. So for triangle ABC, is each segment AD, EG, or CF a median and altitude, or neither? Explain. So let's look at AD is a segment that extends from vertex A to CB, which is opposite A. I believe that. AD meets CB at a point D, which is the midpoint of CB. CD is congruent to DB. So it looks like that's going to be a median. AD is not perpendicular to CB. So it's not an altitude. It's neither an altitude or median. So it's a median. All right. It cuts CB in half, and it's coming out of vertex A. Circle the correct statement below. So AD is a median. What is the correct description of EG? EG does not extend from a vertex, so it's neither a median nor an altitude. And by looking at it, it appears to be a mid-segment. Mid-segment, but I don't know that for sure because I don't know if AG is congruent to GB. Let's look at the next, finish this problem. CF is a segment that extends from vertex C to AB. CF is perpendicular to AB, so CF is an altitude. All right, now what about concurrency of altitudes theorem? We've learned about concurrency of angle bisectors, concurrency of perpendicular bisectors, concurrency of medians, so the last one's going to be concurrency of altitudes. The line that contains the altitudes of a triangle are concurrent. The point of concurrency is called the orthocenter of the triangle. The orthocenter of a triangle can be inside or outside the triangle. So we're going to draw an example of each type of triangle on the coordinate plane below. There's an acute triangle, there is an obtuse triangle, and last but not least, a right triangle. Now, an acute triangle, the orthocenter is always located inside the triangle. The right triangle, it is located at a vertex of the triangle. And finally, an obtuse triangle, the orthocenter is located outside of the triangle. So the altitude of our right triangle in our drawing, the orthocenter is going to be located at point O. Okay. So let's continue on, or point O, the origin. Finding the orthocenter. So triangle DEF has vertices D, 1, 2, E, 1, 6, and F, 4, 2. What are the coordinates of the orthocenter of triangle DEF? So we're going to graph it. All right, we want to underline the correct word to complete each sentence. Triangle DEF is a right triangle, so the orthocenter is at vertex D. The altitude DF is vertical, and the altitude of DE is horizontal, and those are completely backwards. The altitude of DF, where my tools at? Need my pen. What kind of pen it is. The altitude of DF, let me look at that again. Oh, the altitude to DF is vertical. My bad, that is correct. So don't need that anymore. The altitude to DF is vertical. It's Sunday morning. It's been a long spring break. I make mistakes. The altitude of DE is horizontal to DE. So that altitude is the altitude DF. So the coordinates of the orthocenter of DEF are 1, 2. So it's the point D. All right, so let's sum up everything we've learned about triangles and their bisectors. All right, so we're going to use the words altitude, angle bisectors, medians, and perpendicular bisectors to describe the intersecting lines in each triangle below. The end center is the point where if I drew a circle, it would be inscribed within the triangle. Is caused by angle bisectors. As you can tell by the drawing, all three of those angles are cut in half. The orthocenter, which we just learned about, is where the medians, altitudes come together. I should have known that by the perpendicular marks on each of the opposite sides from where the line originates. And then finally, the centroid, it's cutting all the opposite sides in half, and it comes out of a vertex, so it's a median. Got that one right now. And the circumcenter, again, if I put a compass point on the circle, on the point, drew a circle, I would see that the circle intersects the triangle at the vertices, so the circumcenter is perpendicular bisector. So let's check our lesson here. Orthocenter of triangle ABC lies at vertex A. What can you conclude about BA and AC? So what type of triangle whose orthocenter is located at a vertex? That would have to be a right triangle. Sides are segment BA and segment AC are the sides of, again, look at the point they share in common, angle A. So what conclusions about BA and AC can we make? BA is perpendicular to AC, and triangle ABC is a right triangle, and vertex A is the right angle. So that's our lesson for today. When we come in tomorrow, we'll work on some problems with medians and altitudes. We're going to pick up the speed this week, and you'll probably have a test by Thursday on chapter, actually earlier than that, Wednesday on chapter 5. Hope everybody had a good spring break. See you tomorrow.